Hello all. I hope you can hear me. Today is the fifth day of our live coding session. Okay. So in this coding session, we will go through the BERT architecture. It is one of the model which is based on the transformer. And after going through the architecture of this BERT model, we will do the email spam classification. Okay, so this is our use case, email spam classification, and we will do this by using the BERT. And in the end, you will find that without training BERT on our data. Okay, so we will not provide any training data to BERT, we will use transfer learning. Means BERT is already trained, so we will use that only, and we will see that how good is BERT performing. Okay, so let's connect it first. Okay, it is connected now. So just a second. Okay. Okay, so first of all, table of content means what we will cover in this live session. So we will see BERT model, and then we will see the introduction of BERT, then the architecture of the model. Actually, it is encoder based model. Means in transformer we have means a group of decoder, and then we have group of encoder. So that part also we will see that this is encoder only architecture. Then we will see our problem statement. Then we do the data preprocessing. Then we build our model, and we evaluate our model, means how our model is performing. And then we will conclude. Okay. So let's start with a BERT model. So BERT introduction. So BERT is basically bidirectional representation. Here it should be from, okay, not for. So bidirectional representation from transformers. Okay. It was proposed by Google research team in 2008 to 18. And for what? For Google research related queries understanding. Okay. Um, Now see, BERT is actually an encoder stack of transformer architecture. If you have some basic idea about the transformer architecture, then a BERT only has encoder stack of transformer architecture. Okay, BERT presents one of the latest technique for NLP state-of-the-art task in worldwide variety using transfer learning in NLP. Okay, transfer learning is what we train our model, and then we save that model with their parameters, and we can later we can use that model. So that is transfer learning. Okay, now it enables everyone to build machine learning model involving NLP by using this powerhouse. Okay, so and also we would have gone to train, we don't need to train NLP model from scratch also. Okay, in this use case also we will not train our model. Okay, and still it will give very good quality results. BERT is trained bidirectionally, which help it to get deeper sense of language context and flow. Okay, so it is like bidirectional means it is trained from left to right, also from right to left. Okay, so in so that it have better language context. Okay, now let's talk about BERT architecture. So BERT was released in two sizes. Okay, One is BERT base and another is BERT large. So it is the difference of size only, or you can say parameters only. So in BERT large we have 24 layers, and in BERT base we have 12 layers. And the hidden size of BERT large is 1024, and here it is 768. Attention heads are 16 in BERT large, and it is 12 in BERT base. So if we will see total number of parameters, so those are 340 million in BERT large, and it is 109 million in BERT base. So output from BERT model. So this is the thing, like it is the encoder only architecture, and encoders are stacked. So in BERT base, sorry, 12 in encoders are stacked one over another. Okay, so this is BERT. BERT use pre-trained token embeddings and learn positional embeddings. So uh, BERT, what uses it use pre-trained token embeddings and learn positional embeddings. Okay, uh, means there is one token embeddings which is already pre-trained on large number of data. So that it will use. The input representation for BERT. The input embeddings are the sum of token embedding, segmentation embedding, and positional embeddings. So we will use a preprocess from BERT model, which is given by BERT model. We will import. So what we will do? The input representation should be like this. It should have token embeddings, segmentation embeddings, and positional embeddings. And for all these three, I we will see later in our current session only. So now, how to use BERT? So BERT can be used for a wide variety of language tasks, while only adding a small layer to the core models. Okay, so it can be used for many tasks. Classification tasks such as sentiment analysis are done similar to next sentence classification by adding a classification layer on the top of transformer output. So here what we can do classification task by only adding a classification layer, and this thing we will do in this session only. Then for question answering task. So for question answering task, the software receive a question regarding a text sequence and is required to mark the answer in the sentence. Means uh, we were given with one question and then a one text sequence, and we need to mark the answer in this text sequence. Means from starting this point to till this point is the answer of given question from the given text. So there also we can use BERT. So using BERT, a Q&A model can be trained by learning two extra vectors that mark the beginning and end of the answer. Okay. Last in named entity recognition, means what happen in name entity recognition? A software receive a text sequence and is required to mark the various types of entities, like is it person name or organization name or is it date, etc. appear in the text. Okay. Uh, Using a BERT, a NER model can be trained by feeding the output vector of each token into a classification layer that predicts NER level. Okay. So we can do. Now this our current use case, the problem. Okay. So Uh, the dataset consists of email categorized as spam or not spam. Okay, so we have a number of emails which can be categorized as spam and not spam. The dataset has two columns. Okay, so in our dataset we have two columns. First one is category. in which category is mentioned like spam or ham, and another is message in that the body of email is written. We have to build a model which is able to differentiate between spam and ham emails based upon email content. Okay, so it is self-explanatory line. I don't think I need to explain in detail. We will be using BERT to build the spam classifier model. So we will be using BERT to build the spam classifier model. Okay. Now come our most loving part, coding part. Okay. So now we will start with data pre-processing. So I have write down comments, and based on these comments we will write our code. Okay. So let's start. And guys, if you like this video, means videos which I am uploading, so kindly like the videos and subscribe and share with your friends so that they can also watch this. Okay. Now come back to our code. We will be uninstalling TensorFlow text, and TensorFlow hub so that we can install their required versions. Okay. So pip uninstall uh, TensorFlow, TensorFlow text, and TensorFlow hub. Okay, and we keep it quiet. Okay, now pip is install TensorFlow, and what version is required? This one. Keep it quiet only. Okay, pip install TensorFlow text, TensorFlow text, and what should be the version? This one. Keep it quiet. Now pip install uh, TensorFlow hub, and version will be 0.10. We are using this TensorFlow hub so that we can import this BERT model from there. Okay, so run this. Okay, we don't need to provide comma. Okay. Now TensorFlow text is an official library in TensorFlow ecosystem that provides a wide range of text processing operations and utilities for NLP tasks. Okay, so you can go through this documentation also. I am not going through it right now. So we are simply downloading and then importing it here to help us import the word layers later in the code without throwing UTF-8 encoding error. So we are importing it so that later we won't get UTF-8 encoding error. Okay. Now uh, import numpy as np, import pandas as pd, uh, import cword as sns, import matplotlib.pyplot as plt, import TensorFlow, STF, import TensorFlow hub as hub, import TensorFlow. Okay, it is TensorFlow. How will be TensorFlow? How is it? TensorFlow text. Where is TensorFlow text? Okay, TensorFlow text as uh, text. Then we need to, after text we need to import to from TensorFlow dot utils. Okay. Dot utils import to categorical. Categorical. Okay, not from TensorFlow, from Keras. We need to import from Keras dot utils import to categorical. Okay, and then from sklearn import the processing. Then from sklearn dot matrix import classification report. Confusion matrix. From sklearn dot model selection import train test split. Okay, and from sklearn dot matrix dot pairwise. From sklearn dot matrix dot pairwise import cosine similarity. Okay, so let's run this. Okay, uh, TensorFlow how is import TensorFlow how we cannot import name of the database. If we are importing okay, so I think let me run this again. Okay, so this error is coming. Could not find the version requirement TensorFlow from version. Okay, so I think requirement is not matching for this version. We need to update this version, I think. Okay, so check it once on ChatGPT, and if that is the case, we will try to resolve that. Okay, so we can use, I think, this version also, but let's see what's the actual issue. Most probably, it is due to the I think this version is very outdated only. ये पर है compatibility भी जिससे है okay, so we will use 2.18 only. Okay, like I said, so run this. Okay, it is running now. So guys, it's happened in real time scenario. Issues happen, but it's okay. Since we are doing live coding, so it should also be the part of that. Let it run. Okay, so now it ran successfully. So run this also. Cannot import name as creator. Tensor. No, no. Let's check also why this error is coming. Okay, because you install old plugin. Okay, TensorFlow how? Okay, so we will install this one only. I hope it is correct now. So now, okay, on the TensorFlow. So let's restart the session. Okay. So let's run this now. How TensorFlow text is causing the issue. Uh, if you import it due to missing package, you can manually install dependencies. Uh, okay. I hope it won't ask to restart the session. Otherwise, there will be issue. Okay, great. Let's see. Now we will run this. Cosine from scalar dot a matrix dot pairwise import. Okay, cosine similarity. Okay, run this now. Okay, now great. It ran successfully now. Okay, now we will import our data and store it in data time. Okay, now uh, we will read this data from this URL and save in data frame. Okay, then we will see the first five rows of our data. So pd.read csv, then data URL, then df.add to see the first five rows. So in our data, we have two columns category which have ham and spam, and then we have message. Now we will do the data pre-processing. Let's check the spam and ham distribution in our data. So it is a data frame name is df. Okay. So df dot goes by and then uh, category. All right. We describe. Okay. So we can see that for ham category there are 4,825 rows and unique are 4,560. And the top is in frequencies. Sorry, I will call you later. For spam, there are the only 747 rows. So, see, the data is in imbalanced here. What I mean by imbalanced, that if there are two categories and one is dominant, means like ham is too many samples and spam has very less samples. So, what will happen? Model will learn too much about ham, okay, and it will be lagging in spam, in lagging for spam. So we need to make our data balanced. So we will do that also in our case. Okay. So now checking the category count. So we have what So ham is this much and spam is this much. Now we plot the plot distribution of categories using CBORD. So SNS dot this plot this plot TF this one this category dot value count. Okay. So it is array and brings color type color that it be default only. So run this. Okay. Need to mention this value counts here as and or this not. Okay. So now you can see category ham has this much count and category spam has this much count. As you can see from the graph and the describe function as well, that the data set is unbalanced. Okay, the spam class has significantly low number as compared to ham. To solve this issue, we can use various techniques of undersampling or oversampling, like smooth. But smooth will not work here because it is not like any numerical data. It is text data, so is smooth will not work here. Okay, so for this notebook, what we will do, uh, we will do a sampling from larger class. Okay, so from ham, we will take samples equal to the spam and then we will proceed because we have time constraint also. So that's why we will follow that only. Okay, so we will serve the purpose so that we can understand the BERT. Okay, sampling from the data to balance the data set. So, okay, now filter spam rule. So it is saying that filter spam rows and df storing df. Check the shape of df spam dot shape. Okay, so this is the thing. Now filter the ham rows from df and store in df ham df category equal to okay, and then show the shape of this also ham dot shape. Okay. Sampling equal number of data is spam from ham data frame. Okay. So what we need to do, sample ham goes from df ham and store in df ham where df is spam sample. Okay. So df ham dot sample and then df spam dot shape. We will take 0 because we need to take in the shape. First is rows and second is column, so we will take rows. Okay, and then we will show the shape of this dot. Okay, so now we will concatenate the df ham sampled and df spam using pandas and store in df valence. So df valence equal to pd dot concat, and now df ham sampled comma df spam. Okay, so we can see this function also concatenate pandas. Okay, so here it is. Let's see. So pandas dot concatenate objects, x is equal to 0 and join will be outer by default, ignore index will be false, keys will be none, like this it will be. Okay, so you can go through it. So here just concatenate these two and join how to handle indexes on other axes. Okay, so just run this. Now check the value count again. Df balance dot value count. Okay, Df balance category dot value counts. So now our data is balanced, and we can see also here SNS dot displot Df balance. Okay, so let's see the 5 samples of Df balance. So this is the category. I am leaving my house now. So like this. Okay. Now encoding comes in. As the category column is still variable, we will simply encode it to numerical class. We will put 0 for ham and 1 for span. Okay. So what we will do, this categorical column, we will do one hot encoding. We will put ham for uh, or label encoding, you can say, uh, 0 for ham and 1 for spam. So create spam column in df balance. Okay, using 1 for spam as 0. So we will use lambda function here. So df balanced now dot category dot apply lambda x. 0 if x dot if x is equal to uh, m as 0 for x and so will this work? So it makes everything as 0 for spam also. It makes 0. So means what mistake we have done in this function? The balance category dot apply lambda x of 0 if x equal to spam. Oh my god, else 1. Okay, so now you can see for spam it is showing 1 only. Now splitting the data. So we will creating the training and test side now. So split DF balance message into and DF balance into this much. Okay. So X train, X test, Y train, Y test. Train test split. Now X balanced, DF balanced, spam test size would be 0.2 and since we have already tackled that unbalanced data. But sometimes if we don't tackle that unbalanced data, in that case, we can use stratified also. Okay, so stratified make sure that in splitting, uh, equal distribution should be there. Okay, so it should not happen that since if any category is less, it goes into train only, or won't come in test, or it goes to test only and won't come in train. So for that, we mention uh, stratify, and also for stratify, we need to mention for which column we are talking about. Okay, so DF balanced, and then spam. Okay, so 1 second. Okay, so run this now. So the head it is now we will do the model building. First of all, we will importing BERT model. As we have established that BERT is a pre-trained model, we will import this from official site. Okay, uh, and there we are going to import pre-process, uh, and then we will import encoder part. And this is the link. You can go here and read about it. As we have already established that BERT has two sides, so we will use a BERT base here. A BERT leverages a transformer architecture. It enables it to model the context and relationship between BERTs in a bidirectional manner. The larger number of hidden units, 768, help BERT capture complex patterns. More the number of hidden units, more complex patterns any model can capture. Semantic relationship and contextual information in the text data it is trained on. So this is BERT base and this is BERT large. Here 12 encoder are there in BERT base and in BERT large we have 12 encoder, sorry 24 encoder. We will be using BERT base for our classification model. The pre-processed part of BERT refers to the text pre-processing steps performed before feeding the data into the BERT model. As already established, this part helps us to perform tokenization, adding spatial tokens and attention masking. Okay, so what preprocessor do? It help in tokenization and it adds spatial token and also add attention masking. Okay, so the encoder part of BERT here help us leverage all the pre-trained uh, BERT layers for the output we are targeting toward. It consists of the hidden unit layers, attention layer, and 12 transformer part stacked. Okay. Now importing the encoder and preprocess layer from TensorFlow Hub model for TensorFlow 2. So, so we will import BERT preprocess and BERT encoder. Okay. So for BERT preprocess, we will do TensorFlow dot sorry hub. We import from TensorFlow hub. So hub dot keras layers, hub dot keras layer, and then on the path we will provide for encoder also. We will import layer and sorry, which is in quotes only. Okay. So for word encoder also, we will import encoder layer and import in word encoder. So hub dot keras layer and then this. Okay, it is also giving error. So let's see what's the error. स्मॉल टाइप करने होता है ओके तो it should be keras layer. dot keras here. Okay, run this. Okay, it is running now. Let's wait. Let it complete first. Okay, so it is done now. These two variables start behaving as a function now. Okay, so now when we save these layers into this BERT preprocess and BERT encoder, so these two will variables will behave as a function now. When we import them using a Keras layer, that simply means that you can give a bunch of input using them and get desired outputs. Okay. So let's take an example to understand it more clearly. For example, we have taken example test. I love Python programming. So using the layer as a function, apply word preprocess on example test and store in T. Okay, so word preprocess, word preprocess. Okay, and then provide example test in it. Okay, sorry. Uh, As this will return a dictionary, let's print the keys and see what's it all about. Display the keys. Okay. So we will see the key dot keys. Okay. So run this. So here you can see that this dictionary has input type IDs and input mask and input word IDs. This is the keys which we have from BERT preprocess. So input type IDs and input mask and input word IDs. Let's break this down to establish a clear understanding. Okay. So if we will print input mask, so it will show something like this. Okay. So its shape is 1 comma 1 to 8. Okay. And data type is int32. Here in the shape 1 comma 128, 1 signifies the number of sentences in the input. Okay, that is 1 in our case, and 128 is the maximum length of sentence for this model. So this will be the maximum length of sentence for this model. So we can give up to the 128 length sentence. If we take a closer look at the first few numbers in the array, it shows 6 ones, but our sentence only has 4 words. This is a great time to remember that special tokens that we studied about CLS and SAP tokens, which makes it a total 6. So at the starting of every at the starting of our input, we use CLS token. Okay, and for the separation for between two sentences, we use SAP token. Okay. Okay. So this is the input mask. The input word IDs and input type IDs are simply the IDs of the word that are used in the sentence. If you have multiple sentences, they are very useful. In the below code, it clearly shows the IDs of the words in the sentence. So if you will see input IDs, So these 101, 1045, and this like this is there. If you see this 101, so this is the input word ID for CLS. Okay, and this 102 is the ID for this SAP. So these will remain standard only. For CLS and SAP, it always fixed as 101 and 102 respectively. And rest are for the words in our sentence. Moving on to the encoder part. Okay, so I hope you are clear with the pre-processing. Three keys are there: input type ID, input mask, and input word ID. Now that the text is pre-processed, we need to pass it through BERT model in order to get an output which is in the form of a vector. This is exactly what the encoder layer we just imported does. Let's continue the same example to understand this part as well. So, passing the pre-processed text through the encoder. So, example test. What is the name? Word encoder. Okay, and I think T was T. Okay. Okay. So, like this, we do and see the result of the keys of result from the BERT encoder. Pulled output, then sequence output, encoder output, and default. So we have pulled output, sequence output, encoder output, and default. Okay, we will see this one by one. All of these outputs are embedding vectors. So all of these are embedding vectors only. The embedding vectors we are going to utilize is the pulled output, as it's the representation of the entire input sequence. It is generated by applying a pooling operation, typically min or max pooling, over the sequence output. So whatever we are getting from sequence output, we apply pooling operation in that, and then we get pulled output. Uh, we can also use this embedded vector for various NLP tasks in our text classification. So this is our pulled output looks like 1 comma 768, because 768 heading units are there. As you can clearly see, we are getting an embedding vector of length 768, as we are using the base BERT model with the same number of hidden units. Here, one is the shape signifies the number of sentences in our case. Encoder outputs typically refers to the entire output of the transformer layers in the model. So what it is saying that the encoder output is typically refers to the entire outputs of the transformer layers in the model. Okay, sequence output refers to the output of the last layer of the transformer in the word. It represents the contextualized representation of each token in the input sequence. This is the base of pooling vector. In general, default a default can refer to the default value setting or behavior that is used when no other value or configuration is specified. Therefore, basically the sequence output is the last layer of the encoder output, because encoder output refers to the entire output, and sequence output is the last layer output. So example result encoder outputs -1 means last output is equal to the example result sequence output. And if we run this, it will show true everywhere. Okay. Now that we have a clear understanding of concept that we are going to use behind building our classification model, let's build some functions. Okay. Uh, Creating embedding vectors. We will create a simple function to get the embedding vector of the input provided. So what we will do, we will create a simple function to get the embedding vectors of input provided with the help of BERT. So uh, okay, so now create the function to get the embedding vectors as seen above. We will use uh, pulled output of the input provided. Okay, okay. So let's follow these instructions. Define a function get sentence embedding. Def get sentence embedding and with input sentences. Okay. Uh, Preprocess sentences using word preprocessor and store in preprocess text. So preprocess text equal to word preprocess word preprocess sentences. Now return bold output from word encoder using preprocess text. So now return preprocess text, and then in that preprocess text, and in that we uh, mention bold output. Okay, so preprocess word preprocess sentence return return the pulled output from word encoder. Oh, okay, preprocess text, and in that also pulled output. Okay, so like this we do. So run it. Uh, this function will return an array of 768 length. Checking out the function, so we will check out get sentence embedding and then $500 discount. Hurry up, hurry! Are you up for volleyball game tomorrow? Hurry! So run this and see. Okay, so this function is working correctly. So what we do, we define one function, get sentence embedding. We are providing sentences as an input. If one sentence is there, okay. If more than one are there, we can provide them in the list. Okay. Then we do. apply a word preprocess on sentences and save them in preprocessed text. Then we apply word encoder on preprocessed text. Out of all the output, we take code output. Okay, so this is the thing. They show that function is successfully created. Is successful in creating the embedding of the provided input. Now, uh, we will see about cosine similarity. Okay, let's take a 1 minute break, guys. Just a minute only. Okay, let's continue. One of the important aspect when it's come to NLP is to understand the context of the word. Means what is the context of the word with reference to other words. Once a word has encoded the input text into contextualized representation. Okay, uh, cosine similarity can be applied to measure the similarity between two vectors in the representation space. It calculates the cosine of angle between two vectors or word vectors which represent a sentence vector and the output vectors which represent their similarity or relatedness. Okay, using a cosine similarity with a word encoded representations allow us to compare the semantic similarity or relatedness between different sentences. So, by using cosine similarity with word encoded representations, it helps us or allow us to compare the semantic similarity or relatedness between different sentences, words, or documents. It is commonly used in tasks such as information retrieval, question answering, and document similarity matching. So if angle is close to 0, so cos value will be 1. It means vectors are similar. If angle is close to 90 degree, so vectors will be orthogonal. And if angle is close to 180, cos will be -1, and it means it will be opposite vector. So like this, we can find out. Now, let's understand this. We will get embedding vectors for a few sample words. Okay. Example, get sentence embedding for banana, grapes, mango, Jeff Bezos, Elon Musk, and Bill Gates. These three are fruits name, and these three are related to tech giants. Okay. So run this and store this in example. Now calculate cosine similarity between example 0 and example 1. So cosine similarity between example 0, that is banana, and example 1, that is grapes, and it should be very high because both are fruits only. So if we will run this, 1 second. Okay, them as one vector only. Okay, so run this. Okay, you can see that cosine similarity is 0.99. That is, values near to 1 means they are similar, and 0 means they are very different. Above, you can use comparing bananas and grapes. You get 0.99 similarity as they both are fruits. Uh, Now calculate the cosine similarity between example 0 and 3. Uh, Cosine similarity between example 0 and example 1, or you can say example 3. So here comes 0.84, very less compared to this. Now calculate the cosine similarity between example 3 and 4. Cosine similarity uh, between example 3 and 4. Example 3 and example 4. So run this. So see again, this value is very high, near close to near. Jeff Bezos and Elon Musk are more similar than Jeff Bezos and banana, as indicated earlier. BERT has been trained on really a large corpus. Cosine similarity help us to see how well it understands the context and will be able to classify the spam emails based on their similarity. So this cosine help us to understand that our model is able to understand the context or not. So you can see it is doing good with it. Now we will be building the model. We will be using the TensorFlow functional API to build the model for more flexibility. You can read about it more here. Okay, so we there are two types of models in TensorFlow. One is sequential and one is functional. Okay, so in functional, if we have more leverage, or means we can create complex model. Means if we have multiple outputs, multiple inputs. Okay, so in that case, we use functional API. I will try to go through it in the end of this video. But for now, uh, or you can go through the documentation also. But for now, let's continue so that we can complete this notebook. So create a text input layer and store it text input. Okay, so we will TensorFlow dot keras dot layers uh, and then input. We need to create input layer. So input in input layer, we will provide uh, shape and d type. It will be TensorFlow dot string and name text. TensorFlow.keras.layers input shape dtype TensorFlow.string and name of this layer will be text. Now preprocess 10 text input using word preprocess and store in preprocess text. So word preprocess. So we will preprocess this text input and using word preprocess and store in preprocess text. Okay, so word preprocess and then text input. Now come the pass pre-process test to BERT encoder and store in outputs. So now we will pass it through the BERT encoder and store it in the output outputs. BERT encoder and pre-processed text. Okay. Uh, now guys, now come the neural network layers. Add we will add a dropout layer in this to control the overfitting. So L TensorFlow dot add dropout layer with point 1 and store in L. Okay, so TensorFlow dot keras dot layer dot dropout point 1 and name will be dropout. Okay, so add dropout layer with point 1 and store in L. So this dropout layer will be on the outputs of we take old output. Okay, so outputs old output, adding a dropout layer to prevent overfitting. Okay, now we are using this fold out fold output as the input to dropout layer. Okay, and now adding a okay, like this. Okay, now add dense output layer with 1 unit and sigmoid activation and update L. So we will add dense layer with one unit and sigmoid activation and update the L. Okay, so TensorFlow dot keras dot layers dot dense and one layer activation equal to sigmoid and name equal to output output. Okay, so this is the layer and update it into L. Now use input and output to construct the final model. Create TensorFlow model using text input as input and L as output and store in model. So model equal to TensorFlow dot keras dot uh, model and inputs inputs equal to text input and output will be the L. Okay, so we create a TensorFlow model like TensorFlow to keras dot models with input as text input and output as L. So run this. Uh, Following keras layer type keras symbol which we place on equal same as a d type. It does not have extra numerical value. You cannot convert to numpy array. Uh, Input shape d type dot string comma name. So let's see why this error is coming. Try to debug it. Uh, compatibility issue है. आप TensorFlow 2.0 यूज कर रहे हो जिसमें keras 3 आता है. हब keras keras लेयर के BERT प्रीप्रोसेसिंग लेयर keras 3 सिंबॉलिक टेंसर के साथ इशू दे रहा है. सो इशू इंस्टॉल ऑलरेडी किया था. अब कोड में टेंसरफ्लो तो keras की जगह टेंसरफ्लो keras लिस्ट. ओके, तो टेंसरफ्लो keras. Okay, so now we will do one thing. We will import this. Let's see. Now try to run this TensorFlow keras Okay, outputs. Okay, it should be outputs. Okay, so now run this. Okay, it ran successfully. And now check the model.summary. Model.summary. So it will sh- show the summary of this model. Okay, so now let's understand the summary of this model. The model takes input from input layer. Okay, uh, okay. So the model takes input from text input layer here. This text input layer. The shape of the input is none. So its shape is none, which means it accepts variable length sequences of text. Following, we have two keras layer, the pre-processing and the encoding that we have already seen. Okay, so this is two. These are two layers: pre-processing and encoding layers. Then we have a dropout layer. This one, uh, which is simply added to prevent overfitting. And finally, we have a dense layer that produces the final output. This one, output dense layer. In this case, it has one unit. It indicating a binary classification task, which is exactly our goal with the output shape none comma 1. Okay, so this is a therefore we have 769 trainable parameters. 768 are related to BERT layer, and one is for the dense output layer we have added. Uh, so what we have done, we have added one dropout layer on our BERT model and one dense layer. Okay, uh, as per our requirement. And the rest are the BERT parameters which we don't need to train in our model. Now compile the model. Okay, so for compiling the model, first create uh, matrix uh, TensorFlow keras dot matrix dot binary accuracy. TensorFlow keras dot matrix binary accuracy, and name will be accuracy. TensorFlow keras dot uh, matrix dot properties, sorry, precision, and name will be precision here. Okay, and accuracy, precision, and one more we will take we will take recall. Okay, TensorFlow keras dot matrix recall, and name will be recall. Okay, now we will compile. So model dot compile, and optimizer will be optimizer Adam loss will be binary loss entropy That's maybe matrix only. Okay, so like in place of this matrix, these three matrices will be used. So we have compiled our model. Finally, let's fit the data into our classifier model and we will train it for 10 epochs. Okay, so model dot fit x train, y train, and then epochs will be 10. Please ensure you are using keras.utils custom object scope and that this object is included in this scope. So 1 second, let me check. Okay, it should be binary cross entropy. Okay, so now let's run it again. Fit, fit the model. Okay, so our training has started. So after this, once it will be completed, uh, model dot evaluate. We will evaluate our model. Okay, so if we will evaluate, it will give accuracy, precision, and recall. Then we will do model prediction. Predict as test using model and store in y predicted. So y predicted equal to uh, model dot predict as test and we will flatten the y predicted dot flatten and save in y predicted. Okay, so let's see where it is. Okay, let it complete, then we will proceed. Okay, so let's wait for 1 minute. It reached at 10 8 epoch. Okay, at 9 accuracy. You can see that it is getting great accuracy, precision, and recall. Okay, it is completing now. Let it complete, then we will proceed. Okay, so now it is completed. Now we will evaluate. For evaluation, we will use X test and Y text test, and then okay, so if we evaluated on test data. So you can see it is getting good accuracy on test data also. So now do the predict on test and then save in y predicted. Okay. Now setting a threshold for prediction to plot the confusion matrix. Currently it is giving probability. So we need to draw the confusion matrix. For that we will use the threshold. Y predicted equal to np dot where np dot where y condition y predicted greater than zero point 0.5. If condition is true, then 1, else 0. Okay, and then draw, then show y predicted. So let's run this. It is the y predicted. Now we will plot the confusion matrix. Okay, it is about to complete. Sorry guys, today session extended a little bit, but actually this is the huge use case, so it's take time. So calculate the confusion matrix using y predicted and y test and store in CM. So confusion matrix y test y predicted actual y value and uh, our predicted value. Okay, and then plot heat map using sigma1 SNS dot heat map. EM will be the data and what equal to true and format equal to percentage. So run this. Okay. So it is performing great. You can see that the number of these are actual, these are predicted. So number of false positive is 16 and number of false negative is 7 only. Okay. So they show that our model is performing pretty well with the range of false positive to false negative nearly 10. We can course elevate the result. We of course elevate the result by training it on large data set. So we have trained it on very small data set, and we can do on large data set also. So let's plot the classification report also. So classification, and in the classification report we have y test, comma y predicted, and this we will do. Print classification report. Run this. So we can say that precision is 0.95. Uh, we can say that precision is 0.95, recall is 0.89, and F1 score is 0.92. Okay, this is the classification report. Now we will do the inference, means to check how our model is performing. So we have taken some reviews. You can go through it, and if we will do a model dot predict on reviews, so it will give the probability of uh, spam. Okay, so first probability is high, 0.83. Second probability is high, uh, it is spam only. Third probability is high, and these are ham only, so these two have low probability. The highest value in first three classifications shows that classifier model is able to differentiate between ham and spam emails with good accuracy. Okay, so um, this is our use case. So we are able to achieve our about 95% precision. Okay, so this is all for this video.